So, hello everyone. Today we have Arne Mertens, who is going to talk about a colax monoidal approach to quasi-categories. Thank you.
Thank you very much. And thank you for the invitation as well. It's very kind. I'd like to be here. So yeah, let me maybe make this a bit bigger. There we go. So yeah, I want to talk about these quasi-categories. Specifically, they're an approach to enriched quasi-categories. And this is a joint work with my supervisor, Wendy Lowen. So maybe to motivate the whole story a little bit, let me start with a hopefully familiar type of objects, which are DG categories, so categories enriched in chain complexes. And we denote DG-cat for the category over some field, and this field K will be fixed throughout the talk. So this is a homotopy seminar, so I'm sure you're probably aware that DG categories are in a way too strict from a homotopical point of view. That is to say, they have a model structure. The weak equivalences are given by the quasi-equivalences. This is the work of Tabuada. And they also have a symmetric monoidal closed structure. This is the usual tensor product of DG categories. But these are not compatible in the sense that DG-cat is not a model monoidal category. And as a consequence of this, the monoidal structure on DG-cat doesn't descend nicely to the homotopy category. So the homotopy category here of DG category it does have a monoidal closed structure. This was famously shown by Bertrand Towen, who constructed the internal HOM for this monoidal category, the derived internal HOM. But it had to be done very ad hoc, very specifically to the situation. And it's certainly not the case that this internal HOM is just given by the internal HOM of DG categories or something. It doesn't descend nicely to the homotopy category. So that's a bit annoying to work with. You don't get it for free. And a very similar thing arises in the context of infinity categories. So one model of infinity categories is simplicial categories, so categories enriched in simplicial sets. And a very similar thing arises there, and for the same reason. You can give the same counterexample for why it fails. So again, these things have a model structure. The equivalences are given by the Dwyer-Kahn equivalences. This is the work of Julie Bergner. They also have a symmetric monoidal structure, which is a product of simplicial categories. But again, these are not compatible. The category of simplicial categories is not model monoidal. And the solution, if you will, in the context of infinity categories is to move to a different model for infinity categories, which is model monoidal. So simplicial categories can be replaced by quasi-categories, complete Segal spaces, Segal categories. All of these are model monoidal. And so a very natural question will then be, okay, suppose if I instead start with DG categories, can I then find a different model, possibly very analogous to the ones which already exist in the classical case, which is model monoidal, which then is an appropriate replacement for DG categories. And some suggestions have already been made in the literature. So here I've made this nice little table. I always love a good table. On the left-hand side here, we have classical infinity categories. So simplicial categories by Bergner. These are the strictly enriched setup. Then Segal categories by Hirschowitz and Simpson. Complete Segal spaces by Resk. And finally, quasi-categories by Joyal. And on the right-hand side, we have the enriched variant. So where we enrich in chain complexes instead of in spaces, if you will. And there's a very general context in which you can describe all this. Kepner and Haukseng constructed a very beautiful, elegant theory of infinity categories enriched in monoidal infinity categories. And specifically, you can take a look at chain complex enriched infinity categories. And the way they construct it is almost model independent. So whatever model for enriched infinity categories we come up with, it should always fit into their theory to make any sense, really. And so each of these classical models have enriched analogues. The simplicial categories, we can go to DG categories. Segal categories, there's a notion of Segal DG categories, which was introduced by Bacard. But then it sort of stopped at some point, and me, together with my colleague Violeta Borges-Marx, we picked this up again. And this is another project we're working on, and Violeta actually talked about this also at this seminar on the 14th of December. So do check that out. So there we sort of go further into these Segal DG categories. And then on the complete Segal space side, there's a complete DG Segal spaces, which were introduced by Elena Dimitriadis Bermejo, a student of Bertrand Towen. And then finally, what I want to talk about today is this little gap here at the bottom. So what are an appropriate enriched analog of quasi-categories that we can define? So that's what I want to talk about today. This I introduced together with Wendy, and we call them quasi-categories in vector spaces. Now, there's a couple of things I should mention. First of all, we can only ever hope to model with this infinity categories enriching non-negatively graded chain complexes. In actuality, these should be considered as being enriched in simplicial vector spaces, and then through some dot-count correspondence, you can get to non-negatively graded chain complexes, but that's the best we can hope for. So that's a bit of a downside. But they are very closely related to classical quasi-categories, and a lot of arguments that you can make there, you can sort of also do here. And these quasi-categories in vector space, they are based on what we call templicial objects. They are some kind of variant, enriched variant of simplicial objects. And they were also used by Violetta to define the Segal DG categories. So she used templicial chain complexes, and as a subclass, she arose at she defined the Segal DG categories. And then what we are going to do today is consider templicial vector spaces, and as a subclass, we will find these quasi-categories in vector spaces. But I will explain all of this in detail in a second. Okay, so that's the introduction. And here's a bit of an overview of what I want to say specifically. First, I want to recall a few classical facts about quasi-categories. I'm sure most of you are aware, but I'm going to need some specific details about this particular model, so I want to recall them a little bit. And then I will explain what those templicial objects are, and then how to define then the quasi-categories in this enriched context. And then finally, I will speak a little bit about the relation to DG categories. And if there's time, I'll speak a little bit about the work in progress, where we are working towards building a model structure on these objects. So we don't have a full model structure yet for these quasi-categories, but working towards some results in that direction, which I will mention at the end, time permitting. Okay, good. I don't know if there are any questions so far. Doesn't seem to be. Okay. Then I will move on. All right, so the whole classical story of quasi-categories starts with the usual nerve functor, everyone's favorite functor. It goes from categories to simplicial sets. It's fully faithful. And if I have a simplicial set, I can consider the following lifting problem for the simplicial set. Here we have the horn, the jth horn of dimension n, and here we have the end standard simplex. And we can ask whether a map from the horn to x can be lifted to a map from the standard simplex. So in other words, can I fill the horn inside of x? And it's a very classical observation that simplicial set is isomorphic to the nerve of some category, if and only if for any j strictly in between 0 and n, any lifting problem like this has a unique solution. So in other words, every inner horn in X can be filled uniquely. And what is then the idea of a quasi-category? Well, we take this condition and we weaken it by demanding not uniqueness of these lifts, but only existence of these lifts. So for every j strictly in between 0 and n, every lifting problem like this has a solution. And this is a weakening of the classical notion of a category, which we then call a quasi-category. So yes, so we can precisely characterize what the categories, or what simplicial sets arise from categories by this condition. And then a quasi-category in my mind has two aspects. It has a category theoretic aspect and a homotopy theoretic aspect. The category theoretic aspect is very simple. The zero simplices of the simplicial set become the objects. The one simplices become the morphisms of the quasi-category C. And then the two simplices witness composition of the edges of the morphisms. So a horn like this is one possible shape of a horn. This can be filled by the lifting condition, which we impose, this weak count condition. It can be filled to an entire two simplex, like so. This always exists. And then the bottom face here will be considered a composition of F and G. Notice a composition and not the composition, because we only demand this filler to exist, not to be unique. But that's okay, because whatever composition we find will be unique up to a notion of homotopy, which I will explain now. Okay, no, first, the degenerate one simplices will then become the identities of the quasi-category. So this composition exists, but it's not unique. It's unique up to a notion of homotopy, and it's this notion of homotopy. So given two morphisms between the same two objects, they will be homotopic if there exists two simplex like this or like this. And in fact, if you assume this lifting property of a quasi-category, then this homotopy relation will be an equivalence relation, and you can mod it out to get an honest category. So given a quasi-category, you can take its homotopy category, which is an actual category, and it's precisely done by modding out this notion of homotopy to get your HOM sets here. Yeah, so that's sort of the general gist. And we want to be able to do the same thing, but in the enriched context. So instead of starting with an ordinary category, we can start with an enriched category. Let's keep it simple. Let's start with a k-linear category. And this whole story starts with considering the nerve of categories. So the first question would be, okay, what is then the nerve of a k-linear category? And what type of object does it become? Instead of a simplicial set, you would expect to get something simplicial-like, but which is enriched. And a first naive attempt could be simplicial vector spaces. But that won't work very well. In fact, there exists no functor going from k-linear categories to simplicial vector spaces, which is in some way compatible with the classical nerve. This is a relatively easy observation that you can make. So by compatible, I mean that this square here commutes, maybe not on the nose, but even up to some notion of weak equivalence. The vertical maps here are the forgetful functors. Here we have the classical nerve, and above here we have the proposed enriched nerve going from k-linear categories to simplicial vector spaces. But such a functor can never exist. You can never find a functor for which this diagram commutes, even up to categorical equivalence, which is the notion of weak equivalence for quasi-categories. So simplicial vector spaces are not going to work, and you can see it already fail if you look at the definition of the usual nerve. Okay, I'm going to go over this fairly quickly because I think it's quite well known. But if you have a small category and you take its nerve, then the n simplices of this nerve are sequences of composable morphisms. So some f1 to fn, some sequence of morphisms which are aligned at the objects. And the interface maps and the degeneracy maps can be defined fairly straightforwardly. You just take a sequence, make it shorter by composing two morphisms in the sequence, and then the degeneracy maps, you take a sequence, make it longer by putting an identity in the middle. And the outer face maps then, they take a sequence and they make it shorter by either forgetting the first or the last entry of the sequence. You sort of project away onto the first n-1 or onto the last n-1 components. And you can ask, okay, can I do the same thing for a linear category? Well, the same definitions work. Instead of having a product here, I didn't use the tensor product of vector spaces. Instead of a coproduct, I use the direct sum. And very similarly, you can define the interface maps and the degeneracy maps, just composition and plugging in identities. But this fails if you want to define outer face maps. So you cannot define outer face maps in the usual way, because now instead of a sequence of morphisms, I have a tensor product of morphisms. And this tensor product is not a Cartesian product, so I cannot project onto either the first n-1 or the last n-1 components. This map is not a linear map. The thing is that it's written here. So you cannot define these outer face maps, which is the reason why you don't obtain a simplicial vector space. However, we get something different. We do get some co-multiplication maps. We get maps which go from p plus q simplices to p simplices tensor q simplices, taking a sequence like this and splitting it apart as two sequences as such. So the idea is somehow that we want to, in this enriched context, replace the outer face maps by instead co-multiplication maps. And that's exactly how we define these templicial objects, which we'll then use to define the quasi-categories. So this can be done quite generally, given some bicomplete symmetric monoidal closed category V, let's say. So in mind, you should have V, the category of sets or vector spaces, maybe something more exotic like complete joint semi-lattices or something. Mostly we'll consider this V to not have any higher structure, at least in the case of what I want to talk about today. The higher structure should come later when imposing this horn lifting properties and such, just like it's done for classical simplicial sets and quasi-categories. Okay, so how do we move on? What we do is we take the usual simplex category delta, and we take a subcategory which is delta f, category of finite intervals. It has the same objects, namely these ordinals, for any non-negative integer n. And then the morphisms are not all order morphisms, but only those which preserve the endpoints. So for which f of 0 is 0, and for which f of m is n. And then we will consider functors out of this delta f. So what is a templicial object then? It's short for tensor simplicial object. It's a pair xs, where s is a set, and x is a functor like this, coming from this delta f to this category, which is a category of V-enriched quivers with a fixed set of objects, S. So V-enriched quivers or V-enriched graphs. I will, in the next slide, I will unpack this data, explain exactly what this all means. But we demand this functor to be both strongly unital and colax monoidal. And we denote a category like this. Okay, so why do we do this? Well, firstly, the restriction to delta f precisely gets rid of the outer face maps. So this functor will only have inner face maps and degeneracy maps. And then to compensate, we want to add these co-multiplications, and this will precisely be captured by the colax monoidality of the functor. So taking this nerve as a guiding example, we define our templicial objects in this way. Okay, it's a bit of a weird definition, but just as a reality check, let me say that at least you can define a free forgetful adjunction between classical simplicial sets and these templicial objects. And moreover, this will become an equivalence if V is the category of sets. So it really is a generalization of the classical notion of simplicial sets, but in a different direction than simplicial objects. You can take simplicial sets and generalize either in the direction of simplicial objects or in the direction of templicial objects. That's sort of the idea. And I ascribe this being an equivalence to Tom Leinster because, I mean, he didn't show this in this context, of course, but the result is based directly on an observation of his from already a while ago. Okay, so let's unpack this data a little bit. Given such a templicial object, it's a pair xs, where S is a set, and this set should be interpreted as a set of vertices of X. So each element is a vertex, just like a classical simplicial set. I have a set of vertices. And then for any two such vertices, A and B, and any natural number n, I have an object like this. And they are indexed by the vertices here. This is because we were working with that quiver category from earlier. And intuitively, we should think about this as an object of n simplices from A to B. So whose first vertex is A and whose last vertex is B. Visually, you should keep this picture in mind. And then the strong unitality condition from earlier, basically, it's a little bit technical, but it makes sure that the zero simplices of X do correspond to the elements of S in a way. What's more important is that we now have inner face maps and degeneracy maps still. So for any j strictly in between 0 and n, I have a face map going from xn to xn minus 1. And for any degeneracy map of any I between 0 and n, I have a degeneracy map from xn to xn plus 1, satisfying the usual simplicial identities. I don't have outer face maps. This is because we restricted to that delta f category. Instead, to compensate, I do have these co-multiplication maps. So for any k and l, I have a map mu kl going from xk plus l to xk tensor xl. Okay, so intuitively, what does this do? It takes a simplex and pulls it apart into two simplices which are joined at a point. For example, this mu1, 1, 2, it takes a 3 simplex and pulls it apart into a 1 simplex joined at a 2 simplex like this. And classically, we would want to take our outer face map to reach this face, but this I can no longer do. I can only access this face, not directly, but only when it's joined inside this bigger tensor product, only when it's joined at this other simplex. This is precisely because this tensor product is not Cartesian. Otherwise, I could project onto either of the components, but because I'm working with this tensor product, I have to drag everything along. And it's a bit annoying, but it is necessary in order to be able to define these nerves. So that observation from earlier, this is now fixed. For any such category V, we can define an enriched analog, which we call a templicial nerve, which goes now from V categories to these templicial objects, our replacement for simplicial sets. And again, it will be fully faithful, and it will be compatible with the classical nerve, which we all know and love. But we can go further. Also, other nerves have enriched analogs. For example, the homotopy coherence nerve by Cordier. Classically, it goes from simplicial categories to simplicial sets. Here, we can make an enriched analog, which goes from categories enriched in simplicial objects to templicial objects. And again, it's compatible with the classical one. And then finally, there's Lurie's DG nerve, which actually goes back to Bloch and Smith. You can also make a linear analog, which goes from DG categories to templicial vector spaces now. I've chosen the V to be vector spaces here. And this functor will also be compatible with the classical one. And moreover, all of these functors have left adjoints, which can even be described fairly explicitly. So that's all very nice. It all seems to work very nicely. So let's, as an example, maybe go to the left adjoint of this nerve functor. So we have this enriched nerve. It goes from V categories to templicial objects. It has a left adjoint, which is the analog of the homotopy category. I've taken the homotopy category from templicial objects to then V categories. You get an enriched category out of it. So if V is a category of sets, everything reduces to the classical setup, whereas with simplicial sets and ordinary categories, and then expressing that the morphism is the composition of two other morphisms in the homotopy category. This comes from a two-simplex in the original simplicial set, like so. So just to be clear, the brackets here mean homotopy classes of edges of your simplicial sets. So a two-simplex like this, with outer faces given like this and bottom face given like this, expresses that H is the composition of G after F in the homotopy category. But in the linear setup, this becomes a little bit more complicated because we can also express things like this. For example, so now V is a category of vector spaces, and I can make equations like this, where H is not just the composition of two morphisms, but the sum of compositions of two morphisms. So how would you express that as a two-simplex? Well, you can do this because the two simplices in a templicial object have a little bit more freedom. In this case, we don't have these outer face maps anymore. They are replaced by this co-multiplication map. And this co-multiplication map, we can express this property by saying that mu11 of W, which is our two-simplex here, is equal to this full tensor product, this full tensor, like a sum of pure tensors. And the bottom map, we still have inner faces, so this we can express in the same way. So notice this looks a bit strange, right? We have a two-simplex, but the inner vertices here aren't really well defined. We can have multiple edges like so. I'm going through multiple different vertices in the middle, but all of this is still a single two-simplex. So we need to add a little bit more freedom to make equations like this work. And this is a bit problematic that we need these more general simplices, because one consequence of this is that the two-simplex W cannot be represented by a map from delta 2 to X. Classically, every simplex in a simplicial set can be represented by a map from the standard simplex. This is just an application of Yoneda's lemma. And that works because we are working in a functor category. Simplicial sets are just functors. But here, we're not working with functors, we're working with these colax monoidal functors. And so we don't have Yoneda's lemma anymore. And so we have simplices which cannot be represented. But there's a solution to this. We can resolve this by passing to necklaces. And okay, so necklaces, they were introduced by Bauès in the 80s under a different name. I think they were called cellular strings. But they were mainly popularized by Duggar and Spivak in two papers where they describe alternatives for the mapping spaces of quasi-categories. And they use necklaces very extensively there. So it is a necklace. It's actually very simple. It's just a sequence of simplices strung together at their endpoints. So you can see where the name comes from, right? It looks a bit like a necklace. And we also call each of the simplices a bead, just like in a normal necklace. So it's each time a simplex joined at another simplex at a point. So the last vertex of the first simplex to the first vertex of the next simplex. And then we call the category of such things Nick. So why would we look at this? Well, precisely because we encountered shapes like this before. Remember, with the co-multiplications, they take a simplex and pull it apart into a simplex joined at another simplex, but that's precisely a necklace. So indeed, these necklaces can help us describe the structure of a templicial object more easily or more compactly. So indeed, the structure of a templicial object, what is this? This is the interface maps, the degeneracy maps, and then the co-multiplication maps. All of them can be parametrized in the same way using necklace maps. So just like classically, okay, face and degeneracy maps are parameterized by co-face and co-degeneracy maps. But now also the co-multiplication maps can be parameterized by, in this case, a necklace map from this necklace, which is two simplices joined at a point, into a bigger dimensional simplex, like so. So formally, what do we get? Given two vertices of my templicial object, we obtain a functor, x.ab, which goes from the opposite category of necklaces to V. It's a kind of a co-bar construction. It takes a necklace like so and sends it to this object of V, which is this tensor product where the dimensions of the x's here correspond to the dimensions of the necklace here. And then the maps between necklaces are sent to the appropriate composition of face degeneracy maps and co-multiplication maps. So it's a bit of a rearrangement of the structure, but the upshot of this is that we can now describe the structure of a templicial object not through a colax monoidal functor, but through an actual functor. This is just a normal functor from necklaces to V. And indeed, then we again have access to an Ada's lemma, which allows us to say that an n simplex of my templicial object is equivalent to just a map going now from this object to X. This is now a map not in templicial objects, but in this functor category. So again, we can represent simplices by maps. And this is, of course, very important because in the quasi-categorical world, to describe these lifting properties, we want to be able to describe simplices by maps, right? Filling horns is described by a filling condition on certain, a lifting condition of certain maps. So with all this in mind, we can now define what a quasi-category is in this context. Here's again the classical definition of a quasi-category. So it's a simplicial set for which every inner horn has a lift. And we simply replace each word by the appropriate word in the templicial context. So we call X a templicial object, a quasi-category in V, if for all vector spaces, if for all vertices A and B in S, and any J strictly in between 0 and N, every lifting problem like this has a solution. Now, this is a lifting problem not in simplicial sets, not in templicial objects, but in this functor category, because it's there where we can represent simplices by maps. Okay, let me explain a bit what's going on here. So x.ab, that's the construction I showed on the previous slide, this way of taking a templicial object and turning it into such a functor. And on the left-hand side here, we have the horn and the standard simplex. These are just simplicial sets. I make them into templicial objects by applying this free functor. And then I do the same construction on both of these as I did for X, but with respect to the vertices 0 and N instead of A and B. So that's sort of the idea. Okay, now we can define whatever we want. This only makes sense if we have interesting examples. And indeed we do. Like all the nerves, which I showed earlier, these enriched variants of the nerves, all give examples of quasi-categories in V as defined above. So when applied to the appropriate category, the templicial nerve of a V category, the multiplicative nerve of a SV enriched category, and the DG nerve of a DG category. And then secondly, if I have a quasi-category in V, according to this, then its underlying simplicial set, using this free forgetful adjunction, will be an ordinary quasi-category. So it's really sort of a lift, an enhancement of the usual notion of a quasi-category. And moreover, to make the story complete and refer to the beginning. Given, okay, in this case, I would need to put a little bit more extra conditions on V. But if I do so, then this classical characterization of categories in simplicial sets also generalizes this context. So X, a templicial object, will be precisely isomorphic to the nerve of some category, some V category in this case, if and only if, for all strict J strictly in between 0 and N, this lifting problem has a unique solution. So if I restrict to quasi-categories in V for which I have a unique solution, then this will precisely recover the category of V enriched categories. So completely analogous to the classical case. Okay. Next up, I want to talk a bit about the relation of these templicial objects to DG categories, which is what I started the talk with. So for the rest of the talk, I'm going to restrict to the case where V is a category of vector spaces, because that's the only context in which DG categories make sense. So recall this linear DG nerve, which we've constructed. It goes from DG categories to templicial vector spaces. This is this one. And then we have this forgetful functor, which goes from these templicial vector spaces to simplicial sets. And we have constructed it in such a way that the composition of these two things is exactly the classical DG nerve. So the question then becomes, okay, well, how close is this functor to being an equivalence or equivalent equivalence, or what kind of structure is preserved, what kind of structure is lost? So to explain this, let me start with a simple observation. That is that if you have a DG category and you apply the DG nerve, which is a simplicial set, so just classical situation, then this will always inherit an associative multiplication, which looks like this. So a P simplex and a Q simplex joined at their first and last vertices, two P plus Q simplices. So in other words, it's a map which does something like this. It takes two simplices joined at a point and fills it up to an entire simplex. In other words, we know how to call this now. These are necklaces. So in other words, this associative multiplications allows to fill in necklaces. And this can always be done. You can always equip the nerve of a DG category with such a structure. The reason why this works is very basic. You just sort of fill in all of the empty space with zeros, and this turns out to work. So it's a very stupid observation, but it's nonetheless true. And then we axiomatize this idea for general templicial vector spaces. So we call a Frobenius structure a collection of maps which have this property, which I just described on the previous slide. So it's a collection of maps like this, going from xp tensor xq to xp plus q. In other words, it's a bunch of maps which allow to fill in necklaces, satisfying some conditions. So associativity, unitality, a naturality, which means that they are compatible with the face and degeneracy maps. And then also there's some compatibility with the co-multiplications, and these we call the Frobenius conditions. They look like this. The details aren't so important, but the only thing I want to note is that they're very similar to the conditions on a Frobenius algebra, where you also have a multiplication and a co-multiplication, and they have to satisfy some conditions. So it's very similar to a Frobenius algebra, which is why we call it a Frobenius structure. And then you can see that all of the previous nerves, again, all when applied to the appropriate category, will all have canonical Frobenius structures. In particular, this is the case for the DG nerve. Good. And then the main theorem, let's say, is the following. Is if I consider this linear DG nerve going from DG categories to templicial vector spaces, and this will factor as follows. So I do have to restrict here, again, to non-negatively graded DG categories, so categories enriched in non-negatively graded chain complexes. But if I do, then this nerve factors as follows. This thing at the bottom here, this is templicial vector spaces equipped with a Frobenius structure and maps preserving it. And this bottom map here is just a forgetful functor, which takes such a Frobenius templicial object and forgets the Frobenius structure. But then the curious thing is that this vertical map will be an equivalence of categories, not even equivalent equivalence, but like a real on-the-nose equivalence of categories. And what happens here is it's a type of bar construction combined with the Dolt-Kahn correspondence, which is the reason why we only have non-negatively graded DG categories. So the relation between these two things is very clear. They're just the same category, basically. So the question then becomes, okay, what is then the relation between these two things at the bottom? Frobenius structures on the left, and these are quasi-categories which live on the right. What is the relation between these two things? Yeah, okay, so that's a question I just asked. What is the relation between those two things? Because intuitively, they do similar things, right? Quasi-categories, they have this lifting property. They allow to fill in all of the horns, or the inner horns. And these Frobenius structures also express a filling condition in the sense that they allow us to fill in necklaces. So you would expect there to be a relationship between the two, and indeed there is. So as a first order approximation to an answer to that question is the following proposition, which says that if X is a cofibrant templicial vector space, I didn't define this yet, but if there's time, I will come back to this at the end. Then X is a quasi-category in vector spaces, so it has this familiar lifting property, this weak count condition, if and only if it has a Frobenius structure which is possibly non-associative. So I didn't define this either, but what I mean by this is that you just drop the associativity condition in the previous definition. And this turned out to be equivalent. So in one direction, it's maybe not too surprising. This also holds in more generality. So if I would replace vector spaces by a general V, this would still hold. It's the other direction, which is the more surprising part. And it also uses the additivity of vector spaces in an essential way. The idea is somehow that you can, okay, if you have the Frobenius structure, then you can fill in all of the necklaces in a coherent way. And you want to be able to fill in horns. So here I have a picture of a horn. I hope it's clear which face is missing. It's the left one here. And the idea is that you can pull this horn apart into a bunch of necklaces, fill in each necklace separately, and then take some alternating sum of all of these fillers, and then this will be a filler of the horn. And the crazy thing is that this works. So it's a very cute little proof, I think. Okay, this is not a proof, this is just a drawing, but it works rigorously, I promise. So that's sort of the idea. So this necklace, for example, which would cover this face of my horn, this necklace would cover the back face, and then this necklace, which is just a single simplex, but it's in particular also a necklace, would cover the bottom face. And this I can fill in with my Frobenius structure. But then notice that I've counted some things double, like this spine here, and this spine appears in both of them. So I need to subtract it because I've counted it twice. That's sort of the idea, if you will. So I also need to fill in the spine separately and subtract it. And a similar thing goes on at the bottom here. Yeah, okay. Okay, now with the remaining time, excuse me, with the remaining time, I want to talk a little bit about the steps we've taken towards homotopy theory. So as I mentioned, the full model structure isn't established yet, but we have some partial results. So recall that classically, there's a model structure on simplicial sets, which has as fibrant objects exactly the quasi-categories. This was done by Joyal. So the properties are as follows. The cofibrations are the monomorphisms. The fibrant objects are the quasi-categories exactly. And the weak equivalences, there are many different equivalent ways of describing them, but one of the ways is saying that they are reflected by the left adjoint of the homotopy coherent nerve. So the homotopy coherent nerve, it goes from simplicial categories to simplicial sets. The left adjoint goes in the opposite direction, and you can characterize the weak equivalences through this left adjoint. And in fact, this adjunction between the homotopy coherent nerve and this rigidification functor is equivalent equivalence. So really establishing both as equivalent models for the same thing, that thing being infinity one categories. And moreover, this model structure is model monoidal, which is one of the important features that it has. So a very natural question arises, right? Does there exist a model monoidal structure on templicial vector spaces, such that on the one hand, this adjunction of the DG nerve is equivalent equivalence. This would be the analog of what is written here in the classical case. And on the other hand, the comparison to the classical situation of simplicial sets is this equivalent adjunction. So here this LDGK is the left adjoint of the nerve, the DG nerve, and here I have again this free forgetful adjunction from the very beginning. So we'd like a model monoidal structure on this thing, making this equivalent equivalence and making the bottom thing a equivalent adjunction. And we have some suggestions for what this structure can be. We call a map of templicial objects a cofibration if certain latching maps are injective, or relative latching maps are injective. Here, this XDEC N is some co-limit. What it's supposed to model is it's a prototypical object of degenerate simplices, of degenerate n simplices of X. And requiring these maps to be injective basically says that my templicial map is well behaved with respect to the degenerate simplices of X and Y, if you will. This is a relatively natural thing to do, at least in the context of like greedy categories and stuff. And if we apply this to classical simplicial sets, then we recover exactly the cofibrations of the Joyal model structure. That's less important. What is important is that we of course want the fibrant objects to be the quasi-categories in vector spaces now. And then similar to the classical case, we define weak equivalences to be those which become weak equivalences after applying the left adjoint of the DG nerve. So this LDGF. If the image is a quasi-equivalence of DG categories, then we call F a weak equivalence. Okay, so again, the full model structure isn't established yet, but we do have a first order approximation in the form of what's called a category of cofibrant objects. It's a kind of shadow of a full model structure. So if we take these templicial vector spaces and we restrict to the cofibrant objects as defined by this notion of cofibration, then we get a category of cofibrant objects, which precisely means the following points, namely that push-outs of acyclic cofibrations are acyclic cofibrations, and also for the ordinary cofibrations. That also the weak equivalence to satisfy the 2 out of 3 property. That's trivial in this instance, but also important is that every object has a cylinder object. So this codiagonal map can be factored as a cofibration rather, followed by a weak equivalence. So this we've been able to show at least. Then secondly, you can show that this category of templicial vector spaces is locally presentable. And it's also symmetric monoidal closed with respect to the pointwise tensor product. So just like for simplicial sets, the product is pointwise. Here also we can define a tensor product pointwise, and this would be nice symmetric monoidal closed structure. And then finally, and most importantly, if the model structure on templicial vector space exists, then it would be model monoidal. So at least we have shown the compatibility between the model structure and the monoidal structure, which was what we set out to do from the beginning. Okay, and I feel like I'm been faster than planned, so this was everything I wanted to say. Thanks for listening, and I'll be open for questions now.
Thank you very much.